Okay, welcome back to the second lecture of the Hiraku Nakajima. He's going to tell us about Satake, correspondence for affine Lie groups.
Okay, thank you very much for introduction. So I'd like to thank again for the organizers for invitation. Okay, as in yesterday, I put the link to my note in the chat box. Okay, I'll talk about the geometric Satake today. So I explain the statement and I explain how this statement can be proved in A1, type A1 case. And this type A1 case is somehow the building block for more general case. And I will explain general case tomorrow. Okay, anyway, so I'm interested in quiver gauge theory. So I take quiver, Q is quiver, Q0 is a set of vertex and Q1 is edges, and I use following notation. If H is H, then outgoing vertex is OH and incoming vertex is IH. And I take P and W. So this is Q0 graded complex finite dimensional vector space. And then I assign the group and its representation. So G is the product of general linear group, VI. And then it's the space of quiver representation. And also the framing part. So then I consider N to be a representation of G. And I assume during this lecture, assume W is not 0. So the framing is always non-trivial. And I use the following notation. So lambda is basically, lambda determines the dimensions of W's. So dimension of Wi times fundamental. Wi times ith fundamental weight, and the mu is lambda minus dimensions of I times alpha. Alpha is a simple root. And then Fy parameter, so which I denote by zeta. So this is an element of the Lie algebra of TC. So this was Pontryagin dual of the phi1 of the group. And I take the real part and tensor with imaginary cotangent. So this has a complex and real part, and complex part is deformation and real part is scalar parameter. But today I consider only, this is also assumption. I only consider the case zeta so phi1 of G, what is phi1 of G? So G is a product of general linear group. So for each vertex, I have a general linear group. Phi1 of general linear group is Z. So it's Pontryagin dual is C star. So for each vertex, I have one-dimensional space. So I consider this to be tuple of cotangents, but I assume zeta I is positive real number. In particular, so, or maybe times I square root minus 1 in this notation. So the complex part is coded. So deformation, I only consider the scalar parameter. Deformation parameter is set to 0. Okay, and I also have mass parameter. So this comes from the flavor symmetry group. So TF is the quotient of G tilde divided by G. G tilde is a larger group containing G as a normal subgroup. And G tilde is acting on N. That was the assumption. So today, I take TF to be product of torus of the general near group of W, which I just simply denote by this in this way. And there's an additional factor. So for each loop, for each cycles, so we first forget the orientation of edges, and we just consider this as an unoriented graph, and I consider the corresponding first Betti number. And for each cycle, I consider the corresponding C star, and then I let act on N by multiplying those linear maps which is in the cycle. Okay. So anyway, so this is not so important. Maybe I will explain this role, the role of this extra factor tomorrow. But so far not so important. And also, I'm mainly interested in Q is finite or affine case. And in this case, we only have this cycle only in affine type A. So in affine type A, you have this kind of things. So there's one cycle. And so only if Q is only affine type A, this P1Q is 1 and 0 otherwise. Okay. So then I consider Higgs branch and the Coulomb branch. So I first start with Higgs branch. So I denote by MH. So M of H is, this is undeformed one, unresolved. So this is zeta equals 0 case. And I have MH. And for particular choice, this choice, if there is no complex part, then there is map phi. So if you know that the definition of the Higgs branch as geometric invariant theory quotient, then MH is a categorical quotient, MH zeta is GAT quotient, so then there is a map like this. So in many cases, this is a symplectic resolution. Okay, and if Q is Jordan quiver, so this is what I call quiver variety, which I introduced in early 90s. So if Q is Jordan quiver, like this, then this MH is LHM description of UW instantons on R4. And the V dimensions V is instanton charge. Okay, so this is well known. And MH of zeta is its symplectic resolution, which can be also understood as the moduli space of framed torsion free sheets on P2. So we have this kind of moduli space, which is gauge theoretic origin. And the Q is affine ADE. So then Kronheim generalize ADHM description to the case of AD space. So this is R4 divided by gamma Q. Gamma of Q is a finite subgroup of SU2 corresponding to the dinky diagonal Q. And the space is resolution of this space or deformation. Okay. And the equivality is a generalization of these descriptions. And Coulomb branch. But if you consider the quiver Q, which is beyond affine case, then we don't have such a description. So this is generally just the quiver variety, and we don't have any other geometric interpretation. And for Coulomb branch, this was analyzed by Hanani Witten and many people, Kapstein and Jacques, and maybe I miss many people. So these people are physicists, and they, started with physical definition of Coulomb branch, which I don't understand. And the definition which I explained yesterday is a mathematical justification of their definition. And we also, not only we give a rigorous definition, we also check that our definition reproduce those people's analysis of the Coulomb branch. So I will explain some statements which I don't know how to prove, but basically we proved the assertions of those people. So anyway, MC of, so MM is a mass parameter. So this is Coulomb branch, and again you have more than MC. So this is the case M equals 0. And claim is if Q is affine type, then MC or MCM is the Uhlenbeck partial compactification of GQ instantons. Multi-tablet space. So this is multi-tablet space is C2 divided by C2 over LG resolution with hyperkilometric, which is different from the Euclidean. So this, maybe I didn't explain the hyperkilometric structure on AB space. So here at the infinity, the hyperkilometric look is approximated by Euclidean metric on R4 divided by gamma Q. But for tablet metric, it has different hyperkilometric have different asymptotic behavior. But anyway, so I only interested in the complex algebraic structure of the Coulomb branch or Higgs branch. So the hyperkilometric is not relevant for my discussion. So maybe you don't need to distinguish those so seriously for the purpose of my lecture. And GQ is so Q is affine type. So this is classified by ADE, and GQ is a corresponding complex, simple complex group. Okay, and this is rigorously proved by my joint work with Takayama. For type A, for affine type A. By some technical reason, our proof works only for affine type. And for finite type, Q, if Q is type finite type, then instant of instantons, so we get singular monopole. Again, the gauge group is GQ. On R3. So this is when M and M correspond to the location of the singularities in R3, and if M is equal to 0, then all the singularities are concentrated at the origin. And this is also if mu is dominant. Yeah, maybe I cannot explain this condition. So this corresponds to good or ugly condition. Then this modular space of the singular monopoles is isomorphic to slice to the orbit in Grassmannian of GQ in Grassmannian of GQ of lambda bar. So maybe just to recall, affine Grassmannian has orbit decomposition with respect to the action of GQ of Z, GQ of O, and each orbit is parameterized dominant co-weight, and this is GQ of O times T of lambda. And I take the closure of this, so that contains smaller orbits, and smaller one is written like this, and mu is less than or equal to lambda with respect to dominance order. So I consider the smaller orbit and take slice. So maybe this kind of picture. So this is an orbit, smaller orbit, mu, and this is larger one, good of lambda, and I take slice like this. Okay, and this kind of picture appears implicitly in Hanane's series of lectures. Okay, so far any question or comment? So this is a brief discussion of Coulomb and Higgs branch of quiver gauge cells. Okay, I'm interested in the topology of Higgs and Coulomb branches of these gauge series. And so from now, I also assume that there is no edge group. So cycle is allowed, but I exclude the Jordan quiver, which I hope will be clear soon. So the result which I proved in early 90s is the following. So I make a connection between the Higgs branch and representation theory. So I have already somehow introduced implicitly GQ, but I consider the corresponding real algebra. In the above, I somehow little bit not. In fact, I should distinguish this GQ and this GQ because here I consider the finite group, a finite type quiver, and here I consider the affine type quiver. So strictly speaking, I first remove the zero vertex in here and consider the corresponding quiver. Okay. So for general Q, I consider the corresponding group, which could be infinite dimensional. So this is Katsumudi real algebra. Corresponding to Q. So Q is affine. Q is affine type. Then GQ is affine real algebra, not the finite dimensional. Okay. So this is the reason why I need to assume that there is no edge loop. If there is a loop, so I consider this to be linking diagram of the corresponding Katsumudi real algebra. But in linking diagram Katsumudi real algebra, this kind of edge loop is not allowed because this corresponds to the requirement that Cartan matrix of Katsumudi real algebra have 2 in the diagonals. So this corresponds to this absence of edge loops. So anyway, so I consider this real algebra. Then I consider direct sum over mu of the middle degree cohomology of the resolved version of the Higgs branch. So this is middle degree. And this is in fact isomorphic to H top of LH of zeta of lambda mu. So where L of H of zeta lambda mu is inverse image of 0 under the morphism which I explained in the beginning. MH0 to MH. And because this is a symplectic reduction, you have distinguished pointed origin in here, and I consider it inverse image. Okay. And this is not so difficult. And the statement is as a structure of representation. Of gay Q. So in fact, it's not the arbitrary thing. This is which people usually wrote 3 lambda. So this is integrable highest weight representation. And the lambda is highest. And this decomposition is a weight space decomposition. So mu is a weight of the algebra, and this is a weight subspace of V lambda. So this is not abstract result. So I have a concrete construction of the representation. So GQ is has generators, which is usually denoted by EIFI and HIs, and I defined EIs and FIs by using correspondence in the product of those Higgs branches. And by convolution, I construct operator that satisfies the relations of Katsumori algebra. So this is the actual more precise statement. Okay. And for later purpose, so I give a slightly better formulation for mathematicians. So I consider I use the shift theory, so I'm not sure so everybody, all the audience is familiar with that. But anyway, so this is the so-called constant shift, shifted constant shift. On H theta, then I consider this morphism, which I forget to introduce a notation. This is pi, and then I push for this constant shift. And then this morphism is so-called semi-small morphism, has a property, the so-called semi-smallness. And because of this, it decomposes into direct sum of simple perverse shifts. So this is a decomposition theorem of Beilinson-Bernstein during GABA. So I see of stratum tensor with H top of fibers. So I take a point from the stratum and I consider its fiber. So in general, this is not really correct statement. In general, you could have local system on the stratum, but in this particular case, I prove that there's no non-trivial local system occurs. So this statement is precisely correct. So anyway, so this I explained that L of H zeta is maybe I should also say this is Lagrangian. This is Lagrangian subvariety. So typical example is a minimal resolution of CC mod gamma Q, and you have the configurations of P1 in minimal resolution, and L is a this is an example of L. So in that case, I mean Lagrangian property is trivial because it's one dimensional, but so in general, I prove that this is Lagrangian subvariety.
Hiraku,
And
there is
yes,
one question by Aswin. Is an analogous spring action on this cohomology for arbitrary quiver?
Yeah, but so you remember this statement. So this is a weight space, and by the wire group action, so usually weight is changed to other weights by wire group element. So you could have the wire group representation possibly only mu equals 0. And for when mu equals 0, I constructed the analog of spring representation. So in that sense, I mean, slight restriction, it is true, yes.
And I have a question. This stratum is the one you just explained the last lecture. This
so for Q is Q when Q is a finite type, then
finite type, yes.
Q finite MH theta lambda mu is MA. No, not so. This is below. So this is a 0. So MH of lambda on nu, and you nu. But if Q is not affine, Q is not finite, then you have extra. For example, if you consider the affine case, then there's some strata which is symmetric power of this R4 divided by gamma Q. Symmetric power. So this is something like Uhlenbeck space.
I see.
So this is a little delicate, yeah.
Is this related to this Hasse diagram and so on?
Yeah, but I think so. This extra piece is usually difficult to understand. And
okay. For affine type.
I mean, no, I mean, I have a complete description of all the strata in the affine case, and
okay.
For general Katsumudi, Kurawibo, we basically describe all the strata.
I see.
But somehow, how to say? So, for example, in the symplectic duality, so I try to compare this stratification in the Coulomb branch side. Then it becomes a little complicated, and I still don't have a good understanding. So for finite type Q, then I have bijection between strata for Higgs and Coulomb, but in general, I don't understand.
Okay, thank you very much.
Yeah. Let's see, what did I say? So I have some this decomposition theorem, and then this Lagrangian is a fiber over the zero. So zero is the smallest strata. So zero is and L is fiber over zero, right? By definition. Okay, so this is a case of Higgs branch, and I ask what is about Coulomb branch. And in fact, if Q is finite type, so then I explain that the Coulomb branch, at least mu is dominant. I explained that the Coulomb branch is a slice in the Affine Balasubramanian. Then the geometric Satake say that this is related to representation theory of Langlands dual group. But in this case, in Q is type ADE. So there's, I mean, Langlands duality is something trivial. So anyway, so we get representation of the real algebra. But somehow, in view of the Coulomb branch, so there's no big difference between finite type or affine type or arbitrary type. So we make a conjecture. This Braverman think about. So this can be. So we call this as a geometric Satake for Katsumudi algebra.
Where's the Langlands duality is involved? Where the G check is appearing?
Strictly speaking, we first need to generalize quiver gauge theory. That is, so Alex Weeks will explain later today. So in this definition, so maybe I didn't explain well. So we start with quiver. So quiver has orientation, but in when I define the corresponding Katsumudi Lie algebra, so I erase all the arrows, and I just consider the unoriented edges, and I consider this as a linking diagram of Katsumudi Lie. So in this way, we only get the so-called symmetric Katsumudi Lie algebras. For example, for finite types, I only get ADE, not B, C, or F or G.
I see.
So if we want the more general one, then in fact, I try to generalize the definition of Higgs branch for many years for non-symmetric for BCFG, but I failed. But in fact, Weekes and I found that for the Coulomb, there is some simple modification, and I'm not sure. So I explain that or not. Monopole formula also has some simple modification for BCFG, and we can somehow justify their monopole formula by modifying our BFM construction. And that is what Weeks will explain. And then Langlands dual Lie algebra is you just take the orientation of all arrows to the opposite one. That is Langlands.
Okay, thank you.
Okay, let me see what. Okay, but somehow I'm not yet make it precise, this conjecture. So for the geometric Satake, I vaguely explain we get to get the representation of the Lie algebra. But this is much more precise statement. So in particular, I use the formulation of geometric Satake. Many people contribute to geometric Satake, so I cannot explain all the names, but I use the particular construction by Markowitz and Vilonen. So they consider the following. So maybe recall in the Higgs branch side, I use the two space, MH zeta and MH. And MH zeta is a symplectic resolution, I briefly mentioned. And I didn't use a mass parameter. So we should use zeta at least also in the Coulomb branch. So, but how I can use? So zeta is a Fi parameter, and Fi parameter is a Kähler parameter for Higgs branch, but it is an equivalent variable in the Coulomb branch. So in some way, I need to use Fi parameter zeta. So this was in the Lie algebra of EC, but instead I consider this as homomorphism of C star to T of C, and TC acts on the Coulomb branch. So this I explained. So MC is a Borel-Moore homology of the variety of triples, and TC is defined by considering the connected component of variety of triples. And because of this, we have natural action. And I choose zeta as before. Zeta is positive real numbers, and the complex part is equal to 0. So then, so I have C star to zeta. And I'm interested in the action of C star, but because zeta is positive for entries, so basically it is the same. I mean, for example, the fixed point with respect to TC and fixed point with respect to C star is the same. So this is the first part of the conjecture. So I consider MC lambda mu, and zeta equals 0. So this is a fixed point set. This is not a fixed point set. So this is either empty set or a single point. So somehow torus action is very, very strong. And if I consider the fixed point, it is either single point or empty set. And it is a single point if and only if the corresponding weight space is non-zero. And this is equivalent by my construction. So corresponding Higgs branch with generic stability condition is non-empty. So this is the conjecture. Okay. So next, so from now, I consider the case when the fixed point is non-empty. So that means the corresponding equivalent is non-empty. Okay. Then next, I consider the repelling set. So this is a notation for repelling set. 1p repelling. So this is a set of points in the Coulomb branch such that limit when t goes to infinity of zeta times t. So this is the action. So x is flow by this action, sister action through zeta. So this exists. So this is the repelling. So this is the definition. So this is something similar to the Lagrangian, the counterpart of Lagrangian separate in the Higgs branch type. So MC lambda mu zeta, and if you restrict to the regular locus, intersect with regular locus of Coulomb branch. Maybe I didn't say that. So this Coulomb branch is a expected to be hyperkähler manifold, but I cannot produce hyperkähler on the Coulomb branch in our definition. But we at least show that there is a Poisson structure on this Coulomb branch, Poisson bracket on the Coulomb branch, and which is symplectic on regular locus. So this is a symplectic variety. Symplectic manifold. So this is Lagrangian. Yeah, this is somehow well-known result, and the point is this function zeta is preserving the symplectic structure. So it's something like maybe this is illustrated example. So we have C2 natural symplectic form dx h dy, and sister action is something like this, preserving the symplectic form. So the repelling set, so when t goes to infinity, so x must be 0. So this is a repelling set. So this is indeed in this particular example, this is a Lagrangian separative, and this is true in much more general. And conjectures, maybe this is a little technical conjecture. So if you don't, I will explain the meaning of this afterwards. And if you don't understand it, maybe you can just ignore it. But conjecture. This is true for any intersection with symplectic leaves.
Hiraku, there's
Sorry?
a question from Aswin. Should it be Fi zeta or mass in the notation of Coulomb branch?
No. I don't use M. So maybe recall. So this is it's a good question. So in the Higgs branch side, I didn't use M. And in Coulomb branch side, similarly, I don't use M, but instead I use zeta. So the construction looks very different, so at least superficially. But I think that this somehow two constructions are deeply related to each other, although they look very different. But some key players. So I introduced the Lagrangian subvariety in the Higgs branch, and then I'm now trying to explain the Lagrangian subvariety in the Coulomb branch side. But the definition, if you look at the definition, they look very different. So in the Higgs branch side, I consider this resolution and consider the zero fiber.
So is it compact?
So this is compact.
Okay.
This is compact, but this repelling set is not compact. This is always non-compact.
Yeah.
So they look very different. But at the end, I mean, I will explain the conjecture, but at the end, so they will produce the same representation. So in that sense, those two constructions are deeply related.
So the mass parameters are always set to 0. That's
so far, yes.
Yeah.
Tomorrow I will explain for how mass parameters should be understood.
Okay, awesome. Thanks.
Okay, second statement. This is true for any intersection with symplectic leaves. Okay, and yeah, maybe I don't have much time, so I just briefly mentioned a beta formulation. Again, for mathematician, is use again intersection cohomology and so-called Braden's hyperbolic restriction factor. Yeah, maybe tomorrow I will explain a bit more detail. Okay, then main conjecture. So I consider this Lagrangian subvariety. And take direct sum over mu. So again, this has a structural representation. Same representation, same integral of the highest weight representation, and weight space. No, maybe this. I just erase two dies. Okay, then by the previous construction, this is H top of L of H of zeta of lambda mu. So as I said, I mean, it's somehow little similar, but very different construction. As you pointed out, LH is compact, but this repelling set is non-compact. So there's no direct geometric relation between those Lagrangian in Higgs and Lagrangian in Coulomb. But somehow both are naturally isomorphic to the weight space representation. So there's natural isomorphism between those two vector spaces.
The left-hand side is the non-compact, so you just consider some compact supported homology?
No, this is the so-called Borel-Moore homology.
Borel-Moore, okay.
So maybe H, for example, C of H2 of Borel-Moore homology. So this is one dimension. And this is, maybe I'm not sure this is not a good notation. So R2, maybe this. Yeah, again, this is not so. Yes. So X is, for example, R2. Then fundamental class is integrity 2. So X is not compact, but if you consider Borel-Moore, or I mean, homology of cycles, locally finite cycles. So then you get this. So any questions or comments?
Where is this conjecture? What's the motivation of this conjecture?
Well, maybe. So I said in the beginning. So this is known for when Q is finite type. So this is the content of geometric Satake correspondence. Maybe I should say this conjecture is true. Well, strictly speaking, so because we know that this understanding of Coulomb-Match when mu is dominant, so I need to use a result of the Kurilov to relate marginal mu to dominant mu. But so essential point is geometric Satake, in particular, Markov-Petronen. Result of Markov-Petronen implies this statement. And people, I mean, people have been has been known. There are two constructions of the same real algebras, but not so many people expect to generalize the Coulomb-Branch side, geometric Satake side to more general Katsumudi. But somehow, in view of Coulomb-Branch, it's a little strange to restrict to only to finite type case, and because the equivalent side can be generalized to arbitrary Q. And also, I think people now expect this is a one of the concept. This might be a consequence of 3D mirror or symplectic duality. Right. So you have Coulomb branch and Higgs branch, and they are different spaces, but somehow related each other in a deep way. So this is one of the example of such phenomenon. Okay. So let me continue. So now as I promised, I explain examples, type A1. So I explain what are the Higgs branch and Coulomb branch yesterday. So MH of zeta of lambda mu. So this is a cotangent band of Grassmannian. The usual finite dimensional V-dimensional subspace in W. And MH of lambda mu is the nilpotent matrix, square zero nilpotent matrices with some rank condition. And Lagrangian is just this 0, 0 section. Okay. So then H top of LH zeta of lambda mu. Take direct sum. So this is one dimensional because this is just Grassmannian, and there's only one irreducible component, one dimension for each P. But you must be careful that so it could be empty set. P is from 0 to W. So this is W plus one dimensional space. But this is exactly the weight space decomposition of irreducible representation of SL2. So in this particular case, you can, maybe I don't explain how I use the correspondence, but so for each V, I have one-dimensional space, and so you consider the cotangent bundle of Grassmannian V and V plus 1, and there's natural correspondence, and using convolution, you can define the action of SL2. And this each diagonal corresponds to weight space. So this is very natural isolation. Okay, and at this point, maybe I consider the mass parameter. Then now in the Higgs branch side, mass parameter should be considered as the equivalent variable. So again, I consider this action. Then I consider MH zeta of lambda mu, and then I consider repelling set for M. So this is the same, I use the same notation. But now the role of the Fy parameter and mass parameter are swapped in Higgs and Coulomb branches. So again, this is also Lagrangian. And L is compact, so it cannot go anywhere. So this is contained in the repelling set. But in general, this is large. Then you can also show that this H top of this repelling set. And if I take M, this be generic, so which means that TF fixed point is the same as the fixed point for C star with respect to M. So this is so this is also representation by SL2, but in this case, I consider the vector representation. And then I tensor with M times. And as I said, this Lagrangian, compact Lagrangian is contained in this repelling set, and corresponding top degree homology group is a direct summand of this larger Lagrangian sample variety. And this corresponds to irreducible representation. This highest weight double representation is contained in this tensor product. So this is highest. Okay, maybe I don't have time, but just maybe I repeat the explanation of the Coulomb branch tomorrow. But basically, picture is same. So I consider MC of lambda mu and take zeta to be non-negative. Then using the description which I explained yesterday. So from this, you get highest weight called W, irreducible representation. And if I consider the MC lambda, so you have a map like this. So if M generic, then this becomes larger, but somehow larger in a different way from Higgs branch. So this corresponds to Okay, so this, as I said, two construction looks somehow different, and for type A1, you compute both Higgs and Coulomb branch in concretely and just identify with the natural representation C2, SL2, sorry. So somehow this seems to be not explain the actual deep reason of why you have the same kind of construction in the Higgs and Coulomb side. But somehow still, how to say, this is a current status of our understanding of symplectic or 3D mirror symmetry. And so I will explain generalization to arbitrary type tomorrow, and we still have some this kind, how to say, general case is reduction to type A1, and the understanding is somehow not be deeper than the explanation which I just gave. Okay, I stop now. Thank you for attention.
Thank you very much. Questions from audience?
Yes.
So Aswin?
Yeah, thank you, Hiraku. So I one quick question about notation. Is M somehow an integer?
No, M is arbitrary complex number.
M
well, I mean, yeah, M is a tuple of integers.
Okay.
So this TF is a diagonal matrix, and so this is a, if this is T, then this is T of M1 and T of M2 and so on. Something like
so,
that.
but in general, I suppose one can think of M as the real masses, continuous parameters. So
yeah. So I just consider all the entry to be rational number, not arbitrary real number. But then in this construction, only the ratio is relevant. So I can normalize so that all entries to be integers.
I see. And another question, maybe this will get addressed in lecture 3. So in your main conjecture, there was a role for H top of L mu or L lambda, right? So that was the fiber of the resolution on the Higgs branch side. Is there a similar statement involving the fiber of the resolution on the Coulomb branch side?
Yeah, so this I illustrated in the last example. So in the Higgs branch side, I consider repelling set with respect to M, then I get the tensor product representation. And maybe I didn't say much. So I consider top degree homology of a repelling set in the resolution. And take the example. So this is isomorphic to tensor product. So this is the actual state.
Okay.
Somehow, still, I mean, I emphasize again that the role of Fi parameter and zeta parameters are exchanged for Higgs and Coulomb branches.
So the conjecture for geometric Satake for affine Lie algebras is both of these. Like, is the statement for arbitrary Fi and masses?
Okay. Yes, but yes, somehow, but this is a central statement, and once you understand this, the general M is not so difficult.
Okay. Thanks.
Maybe sorry, I should mention. So in the usual geometric Satake, in the usual formulation, people formalize the geometric Satake as an equivalence of the tensor category. So one is the category of fiber sheaves, and the other is category of representation of Langlands dual group. And this is the equivalence of tensor categories. One side is tensor product is given by the convolution product for fiber sheaf side, and tensor product is the usual tensor product representation in the representation side. So I don't explain such a categorical formulation, and I still don't know how to formulate in more general setting, but because we don't have the global affine Grassmannian in general. But somehow except this categorical statement, all the consequence of the geometric Satake it seems to be proved in general. So this kind of construction representations and tensor product representation and so on. Okay.
Any other question? If you have a question, please type in the chat. I would imagine most of people cannot unmute themselves, so please type in the chat if you have questions. So the example you gave is the finite quiver, I would imagine.
Mm-hmm.
Is it affine? Okay, okay. Finite quiver.
Simplest one. A1,
yeah,
type
simplest.
A1, just this one.
Okay. Okay.
But I mean, you know that the Katsumuri algebra is built from SL2s. You have various SL2s, and somehow, so I need to construct the representation in the same way.
Okay, I see. And then this Katsumuri algebra can be constructed by Borel-Moore homology of this product of Higgs branch. I think Lagrangian product of Higgs branch.
What do you mean by product? I consider.
How do you construct algebra?
Yeah, I can also construct the representation. Algebra itself.
Yeah.
Or more precisely, I can construct homomorphism from the universal enveloping algebra of the algebra to some algebra, geometric origin of geometric origin.
I see.
And for Coulomb side, it's a little bit more abstract, but we have similar kind of construction.
I see.
Yeah, that part. So I probably could not explain. I mean, that requires some explanation of the sheaf theoretic terminology.
I see.
Actually, I have a quick follow-up question. Yeah. So in the finite case, I know there's a simple condition on lambda and mu for when these slices have resolutions. Is there a similar condition for more general Q?
So I think I don't know. I guess that maybe. So one of the I think this. I don't have any evidence, but somehow conjecture is MC M lambda mu. I have this map, and this is smooth. And if this is smooth, this is symplectic resolution. Yeah, I think so. This is a conjecture, I think. And so in general, so for example, if Q is, maybe this is the case which you know. So this. So if Q is, you can check both. So this is both equivalent to lambda is sum of minuscule weight. So this result is known independently for Higgs branch and Coulomb branch. You can check both in independent way, but you get the same condition, which is this one. Lambda is the sum of minuscule weight. And in general, I'm not sure this remains to be true. And so for affine type A,
no, is there like a corresponding notion of what it means to be minuscule for a general Q for a Kac-Moody algebra?
There are several. Well, I mean, one of the characterization of minuscule weight is that all the this is a dominant weight, so you consider the corresponding representation, and all the weights appearing in the corresponding representation is a wire group translate of the highest weight representation. That is a minuscule condition. And if you literally apply to affine case, I think there is no such weight. But in affine type A, M contains not only how to say the framing parts, which I explained in the beginning. So M is slightly large. So if you have cycles, then you have extra torus acting on the space. And because I still don't understand this part in general. And anyway, so in the affine type A, I cannot formally use the definitions of minuscule weight, but it is well known that both sides, you have always smooth resolution and the fixed point is always finite. So this means M general. So including this part, including this C star. And for affine case, I will explain the meaning of this extra C star tomorrow. But in general, for general Q, I'm not sure I understand the meaning of this extra C star. So that's one of the reasons I don't know how to formulate this condition in terms of the theoretic condition.
Any other questions? Okay, so if not, let's thank the speaker again. Thank you very much.
Thank you.